Okay. Is it recording? All right. Hi, everyone. Welcome to this talk. This talk is about, my name is Ryan Junejo. I'm a ex-vector researcher now, but maybe currently. I'm also a senior data quality analyst at Cohere. I'm also a math stat student at U of T. And most importantly, I'm all around a very cool guy. This presentation is about Hiera, which is a hierarchical vision transformer without the bells and whistles. I'll get into what that means in a second. But essentially, I spent my summer doing a lot of biodiversity research for machine and interacting that with machine learning. So what that essentially means that I created these different systems, like a bunch of different ones that were essentially created to evaluate species classification systems and see like which ones were performing good, which ones were performing better, as well as making some of my own as well. So I made two really, really big models. One was called Hiera and the other was called OpenClip. Now, both of them work pretty differently, but in this presentation, I'm going to go over Hiera specifically. The reason for that was because I've actually just given this presentation yesterday. I presented it at the Vector Institute's self-supervised learning group, and they were really interested to see what Hiera was all about. And I thought, this is a really it introduces a lot of interesting concepts about transformers, positional encoding, and everything. So I thought it would make a very suitable presentation for the CSSU as well. So I'm just going to get into it a bit, just some like stuff beforehand. I'm gonna break this talk up into a few different parts. Wait, it's not. Yeah. So here's the agenda. First, I'm going to give an introduction. This introduction is going to serve as like a sort of gateway path to people who don't know much about machine learning or even like how transformers work in general. This is going to be like a very, very brief overview. I'm not going to be super technical just for the sake of like everyone's sanity, and also just because the paper itself already delves into a lot of the technical details. There will be some technical stuff on screen, and I'll kind of just breeze through them and go over them. But yeah, I'm going to also give an overview of Hiera, how the key architectural insights are with the model. Then I'm going to go over some results that are posted in the paper, as well as talk about some of my own experiences with Hiera. And then I'm going to sort of just wrap it up and give a conclusion. So yeah, let's get started. So first of all, I'm going to introduce what are transformers and visual transformers, what mechanisms are used in them, and what are hierarchical visual transformers and how are they different. VIT stands for visual transformers, just by the way. So let me just start off with transformers. So a bunch of you might already be aware of what transformers are, but essentially they're deep learning model architecture that uses self-attention mechanisms to process and capture relationships between input tokens. It's very commonly used in natural language processing, and the paper was a very that was introduced, and it was a very revolutionary paper in computer science. If you ask any CS nerd or even any CS grad student, I'm pretty sure they know what attention is all you need is. It was a very famous paper, actually published by a lot of people working on Google Brain in Toronto itself. So that was pretty awesome to see. And fun fact, my boss is actually the guy who wrote one of this paper. He was an intern at Google Brain, and he like helped contribute to the paper. And now he's the CEO of Cohere, which is a multi-billion dollar company. That's awesome. Yeah, so transformers are very commonly used in ChatGPT, Google Gemini, a lot of these natural language processing models that we use in large language models and everything. How they kind of work is that they replace sequential processing with parallel attention mechanisms. They use a stack of encoder decoder layers, and they also capture long range dependencies through self attention. I'll get into what these mean in a second, but just think of it as words kind of go in, they get processed into tokens or vectors, and then they sort of come out as a way for the computer to understand and give feedback, essentially. Um, Next, I'm going to go over positional encoding. So as you can see over here in the diagram, this is like a method used in transformers to encode the positions of tokens in a sequence. So if you were to feed a transformer like a certain sentence, how would it like you were to feed it the words the quick brown fox, for example? Positional encoding is essentially what helps retain the context behind the sentence structure. So instead of fox, brown, quick, duh, it knows that it's given in the order the quick brown fox. And the way it does this is that it uses a mechanism that calculates attention scores between tokens to determine their relevance to each other. So it converts every single word in that sentence into an embedding model. It goes through the embedding model, it becomes a token, and then those tokens are kind of computed against each other to see like where their position within the context is. And it uses a variety of different sinusoidal and different components to it, but I'm not going to get into the technical aspects. Just notice that this is essentially what transformers use and what encoders use to really retain the position of any sort of sentence or any sort of thing. And we're going to come back to this a bit when I explain a bit about vision transformers. So next up, we have attention mechanisms. Now, I've mentioned attention a bit over here in this talk, but what exactly is attention? Attention is a measure of a token's relevance to other tokens, including itself. So the model dependencies without regard to the distance between tokens, and they essentially calculate the relevance of one token with respect to all other tokens of the sequence using the query key and value mechanism. So essentially, this also helps in essentially giving different give different parts of the sentence a bunch of different contexts. So a key aspect of all this is just retaining the context when it sort of goes through these encoder decoder models. Now I'm sort of going to go on to vision transformers. Now, vision transformers are very similar to ordinary transformers, but here they're adapted for image processing by treating the image patches as image tokens. So as you can see over here in the picture, think of like a sort of image. It gets transformed into like to different patches. Those patches get cut up, introduced into an encoder, and then they come out through the MLP head where it gets classified. So it divides an image into fixed size patches and processes each token. It doesn't have convolutional layers, but however, it relies purely on self-attention. And these are very useful, and they're introduced in 2021. They're very useful because they're scalable and they achieve high accuracy with large data sets and self-supervised pre-training. Um, However, there are some challenges with it as well, is that because they do not contain convolutional layers, they also lack local inductive bias, which is handled well by CNNs. So even though visual transformers are able to sort of transform an image and classify it, it's not able to really capture a lot of the small grained fine details. And that's where we introduce another different type of transformer, which I'll get to in a second. So before we get onto that, I'm gonna talk a bit about encoders. So as you can see over here, I mentioned a lot about both the images and text kind of going through this encoder decoder kind of phase. But what does that actually mean? So what an autoencoder is that it essentially takes an input and it goes through this thing called the encoder. The encoder reduces that input to a smaller size, and it captures like the most important features in that image over here. Then it kind of goes through a latent space over here, which is like the middle version. The middle space essentially has the compressed data, and now it goes to the decoder. The decoder tries to reconstruct the original input from this compressed data. And essentially, what the whole purpose of this is that it's used for unsupervised or self-supervised learning, and it enables the model to learn very useful representations of the data. And this can be applied to a lot of different domains, not only images and text, but also even videos as well. And it's used for tasks like anomaly detection, dimensionality reduction, or even feature learning. So it's a very important part of like sort of constructing neural networks, and it's a very important part of transformers as well. Next, we're going to go on to masked autoencoding. So now that we know what autoencoding is, what this masked autoencoding means. Masked autoencoding itself is a very important part of the Hiera paper. So essentially how it works is it's a self-supervised pre-training task where a large portion of the input is masked and the model is trained to reconstruct the missing parts. This is really useful because it encourages the model to learn robust features and spatial reasoning by predicting the content of the masked regions. It's used very effectively in vision transformers to train models without labels, and it handles data efficiency very well. So how it kind of works is over here, you can see right before the image goes into the encoder, a lot of it gets masked by these little gray squares over here. A significant portion of the input, usually 75%, is randomly masked, meaning the model only sees part of the data. Then it goes to the encoder. The encoder again processes the visible parts and it compresses the information into the latent space. And then it goes to the decoder where it uses this latent representation to reconstruct the entire input, including the masked parts. Now, the whole goal for this is that it wants to accurately predict and reconstruct the masked parts of this data. This is super useful because when you kind of go through this process multiple times, the model is trained to minimize the error between the actual masked parts and the reconstructed output. And by doing this, the masked autoencoder learns to understand the overall structure and relationship within that data. Right. Now we're going to go on to hierarchical vision transformers. Now, I mentioned a bit earlier when I was covering vision transformers that vision transformers weren't able to capture the very fine-grained details of that convolution neural networks or other different machine learning applications had. So that's why we introduced hierarchical vision transformers. Now, this is an architecture where the input data is processed at varying resolutions, starting with a high resolution and simple features, and then moving to low resolution but complex features in the later stage. So essentially, it kind of replicates what convolutional neural networks do with images, where it's like it analyzes it from a very like high level at the beginning, and then sort of as the layers kind of go on and get processed, they start introducing more it introduces more fine-grained sort of smaller squares to really process the features. So at the early stages it has a high spatial resolution and a low channel count. At the lower stages over here it uses a low spatial resolution and a high channel count. there's a bunch of different hierarchical vision transformers I can go into. Some are use these different concepts like shifted windows or convolutions. But for the purpose of this presentation, just know that like there are a bunch, such as Swin and MVIT. However, the main problem with introducing this sort of concept to transformers is that they end up becoming very slow. So as you can see over here, as pointed out by the Hiera paper authors, this complexity that ends up kind of getting built up with this ends up slowing the model by a great deal. And so really the problem that Hiera kind of aims to solve is how can we make a hierarchical vision transformer which captures all those like sort of fine-grained details of those images, but still doesn't take a very, very long time to run. And that's where we introduce Hiera. Now, first, what Hero is really composed of is that they took MVIT2. MVIT2 is already a hierarchical vision transformer. What they did was that they kind of stripped it back. They were like, okay, let's take this transformer, let's strip it back of all of its components, and let's add something to it. So over here, this is just like a very quick summary. You don't have to like look too much into like the numbers or anything, but all you need to understand is they kind of replace a lot of what made MVIT2 MVIT2 and just replace them with some default sort of applications. So for example, they replace relative position embeddings, they replace convolutions, they replace max attention residuals, and they added something which I'm going to get to in a second as well, called mask unit attention. And essentially what you need to understand from all this is that a lot of the images, by stripping out all of these things, it was still able to retain the accuracy and even improve the speed by a lot, but it didn't have to give up anything in this sort of sacrifices. And this is because of mass autoencoding, which I'll also like get into in a sec. But yeah, just kind of take this in and realize that like what Hera does essentially takes this transformer, strips back all of its components, but still is able to retain both the accuracy and drastically improve the speed in both images and videos. So, but what is the Hera transformer? Let's get into that. Now, the Hera transformer itself, how it's set up is that modern advances over here, modern hierarchical transformers like Swin and MVIT, they're more perimeter efficient, but they end up being slower. So they designed Hiera to be very, very simple. To add spatial bias and to teach it the same things that convolution neural networks usually have, they taught the model using a strong task like mass autoencoding. So essentially, they use mass autoencoding on this transformer, and they were like, hey, if we use this on Hiera, we don't need all those other things. We can take all of those things out, just use mass autoencodings, and still get as accurate of a representation. So over here, Hiera consists entirely of standard VIT blocks. For efficiency, they use local attention within mask units for the first two stages and global attention for the rest. I'll get into that in a second as well. But just realize that Hiera is essentially the stripped back version. All it uses is a normal visual transformer with masked autoencoding. Yet, however, it's still able to retain all of its accuracy and still prove to be a very useful transformer. So how does the masked autoencoding aspect really work for here? Let's get into that. So mass autoencoding, the problem with introducing it to the other transformers like I introduced, like Swin, is that it's not really compatible with those multi-stage models and the methods that they use. Over here in this figure, they really kind of go over a bunch of different ideas that they wanted to use for implementing mass autoencoding. The problem is that it either deleted the mask units, which are these tiny units for masking. It would either delete them and like cause some issues when going through the loops, or it would kind of break the 2D grid. And they introduced a bunch of different solutions. One was mask feet, which filled in the mask. And the problem with that was that since it was not sparse, it was had a very slow training aspect to it. They added baseline as well, which kind of separated the units in the padding. But it was, and this was sparse, but the padding had overhead. So as you can see over here, they had these like black squares, these black outlines that were very unuseful for especially large amounts of loops. So what Hiera kind of did was that they kind of very cleverly just set kernel size equal to stride. What does that mean? So kernel size refers to the size of the window that moves over the input, and stride is how much the kernel shifts after each operation. So by sending them both equal to each other, like those little windows, it means the kernel window moves by exactly the same amount as its size. So for example, if the kernel size like over here is like 2 by 2, and then the stride is set to 2, the kernel will move 2 pixels horizontally or vertically after each operation, but it won't overlap with any of the pre-processed regions. By setting this in the max pooling layers, here eliminates the need for complex padding or overlap during pooling. This makes the model simpler and faster with less redundant computation. So just realize that like by setting kernel size equal to stride, it was able to really take on the mass autoencoding and process that without having to really rely on max pooling or any of the other things these big convoluted models had. But now what are mask units? So I did mention mask units a bit in the previous slide. Mask units are essentially a larger block or chunk of an image, and instead of looking at small patches, the model divides the image into much bigger units. For example, like each mask unit could cover like a 32 by 32 pixel area. But why even introduce this in the first place? By using larger regions, the model itself doesn't need to process every tiny patch of the image. And this makes it faster and more efficient because it can focus on important larger chunks on the image. So it kind of follows a very similar thing as like the other hierarchical models, where it's like it starts off from a very, very big point of view and then uses local attention on those aspects. And then as it goes down into those layers, it starts using global attention. In the early stages, the model only looks at and attends to these larger regions, and that means it processes the images piece by piece, like you can see over here. And then as it sort of goes on, it utilizes global attention. So as the model gets deeper, it starts to look at the whole image much more globally, capturing the broader context. Oh, sorry. Um, Yeah, that's pretty much it over here. There's also some comparisons to window attention. So window attention performs local attention within a fixed size window, but however, doing this would potentially overlap with the deleted tokens during the MA pre-training. So mask unit attention, which they introduce in this paper, performs local attention within these individual mask units, no matter their size. So essentially, this helps kind of retain the context without having to really worry about any features getting deleted. It's able to be very sparse, but also very useful in the sense that nothing gets deleted, nothing gets none of the context of the image styles ever get lost. So yeah, that was like sort of a quick overview on the key architectural insights of Hiera. And now I'm gonna kind of get into a bit of the results. So what were the results? So the training time, as you can see over here, Hiera was much, much, much faster to train than MVIT V2 or MVIT V2 with mask feeds. So all of these are built on the same base version. The topmost one over here was supervised. The middle one had mask feed on it, whereas Hiera had mass auto encoding. And as you can see for both images and videos, it was much fast. It was 3 times faster on images and twice as fast on videos while training, which already like when you're especially when you're training very, very large models on very large amounts of data, this real like time crunch is super, super important. And it's measured in A100 days. So the NVIDIA A100 is a very popular sort of GPU used to like train these models. But yeah, so as you can see over here, Hiera L was much, much faster than its other counterparts. This table isn't super important, but just know that for using Hiera, they also made a bunch of different configurations. So every single model has like a different number of channels. They did this to really compare it to other different counterparts and just show that even if Hiera was really, really small, it's still super efficient compared to the other transformers in its league. So this really is made to sort of set the comparison, but most of these results are going to use Hiera L, which is Hiera's large version. Um, then here's just a bit of this isn't super important. This is just some MA pre-training of like what different parameters they kind of set was. So I'm gonna kind of skip over this. Video results. So video results were super interesting. Hiera improved a lot on the state of the art by a large amount while being much lighter and faster. As you can see over here in the bold, Hiera was much, much more accurate. Not much necessarily much more accurate, but it was much faster, and the accuracy was either the same or it beat any other sort of transformer in its league, essentially. And this was the same on a lot of different data sets as well. Yeah, these are more sort of video data sets. This was pre-trained on Kinetics, which is a very popular video motion data set. Now on images. Now, ImageNet 1K was kind of used as the baseline to really test how effective Hiera was. And again, as you can see over here, in accuracy, it was kind of dominating. Either it'd be the same or it'd be much more than Hiera and much more than MVIT2 or any of these other transformers. So as you can see over here, it really showed that by sort of stripping Hiera back, it was still able to retain all of its accuracy while being much faster. Yeah, this was the transfer learning experiments. Fun fact, I actually worked on this as well. So I evaluated it on INET 19 and INET 21, which I'll get into in a bit. But as you can see over here, transfer learning took place. Transfer learning is essentially when you take a pre-trained model and you fine tune it on this data set and evaluate it. And as you can see over here, it really kind of outshone all of the other models, especially when it came to accuracy and stuff like the different data sets, even as here it kind of goes down from the high version to the base version. Yeah, so here's a summary of the results. As you can see over here, it outperforms the state of the art on images. And as the Hiera authors like to flex, it establishes a new frontier on video. So it's much, much more accurate and much faster in both of these sort of situations. One key takeaway I kind of want to reiterate on this is that Hiera's paper, although it introduces these new concepts and everything, their aim was not to show that, oh, this stuff is useless. It wanted to show that this stuff is very useful. The other things that the swim transformers and the other hierarchical transformers have. They wanted to show that yes, these things and these changes are necessary, but when you have masked auto encoding and you're able to strip all of those back, then like this sort of combo itself is much more useful and much faster compared to that alternative. So it still showed that there is a need for sort of max pooling sort of some situations. Here I wanted to show that if we use this approach plus mass auto encoding, we could really get a lot more beneficial results while still retaining a lot of that context as well. So that's pretty much most of the talk. A bit of a summary was that Hiera's key contributions, it simplified itself by removing complex components, and it enabled mass autoencoding pre-training, which enabled Hiera to learn efficient spatial features directly from the data. The results were it was 2.4 times faster on images, 5.1 times faster on videos, and it was still able to maintain or improve accuracy due to MAE pre-training. It was super efficient, and a lot of it has future potential for open doors and large scale and real-time applications. That's pretty much most of the talk. Thank you guys so much for listening to that. Since we have like a bit more of time left, and I kind of speed ran through this. I actually go over a bit of what my other presentation was, just to do a quick sort of highlight on what Kiera's contributions were to that. So I'm gonna quickly just change up my presentation for a second. Um, yeah. So this is the wrong slide. Wait. Oh, machine learning. Yeah. Um, Here we go. Yeah, machine learning for species classification. So as I mentioned earlier, I did work on biodiversity classification. I'm not going to go too in detail because it's already kind of a long presentation, but I'm going to go over how I kind of use Hiera in this sort of situation. So yeah, essentially the reason we do species classification experiments in the first place is just to really monitoring biodiversity is a really big challenge, and it's a very the robustness of biodiversity in any specific area is super important to measuring how like beneficial or how well an environment is doing ecologically. And so I kind of evaluated Hiera on both the iNaturalist 2019 and the iNaturalist 2021 data sets. So iNaturalist 2019 had 1,010 species and 2021 had 10,000 species. So I had like a very interesting challenge of being able to sort of work these really huge data sets into my work. Here I kind of just went over here again, and the other model I used was Clip. I'm not going to go over Clip that much, but it is super interesting, so I'd really recommend checking it out. I did put a bunch of data augmentations on Hiera. So when I was using this data set, for example, I put a bunch of different transformations to just really, test the model and confuse it a bit, just so I could get a better result. And here are the results. So I was able to get a peak. I used the Hiera tiny version for this because I did not have the resources to be able to afford such high compute. But I was able to get a peak 0.7% accuracy on Hiera, and I was able to really reduce the loss curve by a bit. Usually it would have peaked even more, but I was only able to train it for about 100 epochs instead of the recommended 300 epochs. Epoch is essentially every single loop. So I was only able to train it for 100 instead of 300. And then for iNaturalist 2021, I was able to get a peak accuracy of 0.6. This is kind of low, but the reason for this is because I used the mini data set instead of the big data set, just because of time constraints. And the accuracy over here peaked at 0.61, which is the same as WaveMix, which was the top performing accuracy in papers with code, which is where we kind of like evaluate a bunch of different models on different data sets. So that was kind of results for Hiera. Yeah, some challenges faced, some lessons learned. I'll kind of go over that as well. So these didn't really have much to do with Hiera, but more with the data set itself. But I feel like these are really important things to kind of go over when you're working with very large data sets. One thing is memory considerations and storage problems. Always asking, I had to like repeatedly ask for a much higher storage, and I had to basically beg them. I'm like, Vector, please give me more storage. But I eventually was able to kind of get like level up into getting using NVIDIA's higher end chips, which was really nice. And that was actually when I was able to start, getting off the ground and building stuff. But before that, I really had to like play around with my memory constraints. I had to do things like making batches of batches of batches to really fix my training set into my model and everything. And sometimes it would be really hard to trace back problems when epochs would take 30 minutes each. So when you have a very large data set, they usually take a really long time. For my case, even though Hiera was super fast, because the data set was so big and I had to really go through a lot of transformations, every single epoch would take at least like 30 minutes. Lessons learned would be to iterate, 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 especially when you're building stuff. I think it's really important to just kind of walk yourself through your code, explain it back to yourself. Stuff that teach you in like your first year CS course, but you never actually listen to until you're actually in the field. Another thing is to get to know your data set, especially large ones like iNaturalist. It's super important to know your data set and visualize what's kind of going on at each step, like I showed in the beginning, just because it really helps you capture the context of what you're working with. Another thing is large datasets take time. Don't be afraid to use more power and higher batch size. That's pretty much it with my presentation. Yeah. Thank you to the Vector Institute for having me, and thank you to Nate and Graham for helping me a lot for working with this. And again, thank you to the CSU for letting me have this presentation. Yeah. Thank you. Sorry if I speed ran a bit through that. I just like I end up talking really, really fast when I present sometimes. Yeah, go for it. For explain for like Hiera, let me introduce myself. I'm a poster researcher regarding the Arduino language model. And recently, some research paper find that the MP5, the encoder decoder model, yeah, have semantically the same meaning in output of the encoder in the among the part of languages. Yeah. So that is, the MP5 encoder encoded one single input into the same semantic meaning, almost same meaning, semantic meaning. Yeah. But I'm just curious if here encoder, have the similar algorithm about the encoder, we will explore the output of the encoder and see, how generation of the inputs are occurred. Yeah, I'm curious about the output of the encoder and the semantic the meaning of the encoder. Wait, are you talking about from like a compute like an image sort perspective, or are you talking about from a text sort perspective? Oh, I mean, but I'm thinking about integrating the word imperative models, right? If here encoders outputs, if here encoders are semantic and meaning of the inputs, that we may apply this semantic meaning for language models, for example, because language models can capture semantic and meaning of the input. And yeah, the probably the language models can use of this semantic meaning and output target value, for example. So yeah, that is why I'm curious having explored the semantic meaning of the encoder. I actually haven't, but that's actually a really good point you kind of bring up because even at Go here they're working on this model called Aya. I'm not sure if you've heard of it, but Aya is also like they do a lot of multilingual sort of exploration on like they built like a lot of good models. I think they've even won awards for Aya as well because of just how